Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hello, everybody. It's my pleasure to welcome Dimitrios. Many of you already know Dimitrios. He's an MSR fellow, and he has interned here in the past. For others, he is a PhD candidate from Yale. Before that, he finished his computer engineering at University of Patras in Greece. He has done a lot of cool work in designing sensor networks for human behavior monitoring, as well as focusing on the design of the sensor nodes themselves for power-aware computing. And with that, to Dimitrios.
Great, thank you very much for the introduction. Really happy to be here. Really happy that you attended my talk. So the topic of my talk will be on power-aware platform design for wireless sensor networks. But before I go into the details, I will try first to give you a general idea of what wireless sensor networks are, even though I know that most of you know that already. Then I will give you a general overview of the work I've done during my PhD. And then I will simply focus on the part of my PhD that has to do with the power-aware platform design. So in the case of wireless sensor networks, what we have is basically a large collection of battery-operated wireless sensor nodes that have limited sensing, processing, and communication capabilities. The whole idea is that every sensor node records locally some amount of information, and that by combining this information over time and across the network, we can perform global tasks. Now, to give you a feeling of what a sensor network looks like, here you can see 4 different sensor nodes. This is a low-power sensor node, the Telos mode for Berkeley, very widely used. This is a more power-aware platform, the XYZ sensor node that I have designed at Yale University. And here you can see the actual sensor node interfaced to a VGA cell phone camera through a prototyping board. This is the IMO2 sensor node interfaced to the same camera through a custom design board I've made back at Yale University. And here you can see the mPlatform architecture, a wireless sensor node architecture that I developed in collaboration with the Network Embedded Computing Group here at Microsoft Research. And this is a modular plug-and-play architecture. The main idea is that you just use individually designed hardware boards with customized sensing, processing, and communication capabilities, and you create application-specific sensor stacks. Now, to give you an intuition of what a sensor node looks like, I've brought some toys with me. So here you can basically see the XYZ sensor node I have designed at Yale University interface to the VGA camera, and you can simply just pass it around if you want to get a feeling of it. This is the mPlatform architecture that I've designed in collaboration with Bodhi and Feng here at Microsoft Research, where you can see that multiple boards are stacked up together to form application-specific sensor stacks. And this is the IMO2 sensor node from Intel with a custom-designed camera board to be able to monitor humans over space and time. Now, these sensor nodes and many other sensor nodes have been used in several different deployments that mainly focus on environmental monitoring and surveillance. Now, these applications and these deployments have really set the fundamentals around sensor networks in terms of very basic problems such as localization, time sync, event detection, and many more. However, if you go into everyday life applications, you're going to see that sensor networks are absent. And the reason they are absent is that we've been designing them so that they can offer services to experts and scientists. What we have to do is we have to focus more onto everyday life applications and to everyday life people. In order to do that, we need to have 2 things. The first one is we have to shift the focus of sensing in this paradigm more to the humans. We have to move from monitoring the environment to actually monitor the humans and the way they interact with the environment. Now, given this information, we have to equip the sensor networks with the necessary capabilities and mechanisms to automatically understand, summarize, and interpret the information to create an understanding of what people are doing over space and time. Now, if they have such an understanding, then they will be able to provide responsive services. Now, my work during the PhD has actually focused on the design and implementation of such a framework for understanding human activities over space and time using a heterogeneous set of sensor nodes. And the main idea is that every sensor node will only observe a portion of the global human activity. Now, by combining this low-level information over time and across the network, we can identify the global activities that the actual humans are engaging into. And based on this understanding, we can generate triggers or provide specific services. Now, the driving application, the main application that has been driving the design and development of this framework has been the assisted living. application. In this scenario, you can assume an actual elder person living alone in a house. The role of the sensor network is to be able to continuously monitor the person, guard against unsafe behaviors, make sure that the person is engaging into activities that he should be engaging, create automated activity summaries and profiles, and try to use these profiles to assist the person in his everyday life tasks. Now, to better understand the challenges that we have to address here, and to create a nice playground for our system to evaluate it, we moved to 3 actual houses in New Haven, Boston, and Cyprus, and we deployed our sensor networks to get real data and monitor real elder people. Now here what you can see is the floor plan, a 2-story house in the case of the New Haven deployment. Now to give you an intuition of what data we're actually recording, here you can see the actual video. Every number here corresponds to a camera sensor node like the one you have in your hands, that is the XYZ with a VGA camera. What every camera sensor node does, it abstracts the person as a dot. Now as the person moves over space and time, what we're basically getting is a moving dot on top of a map. Now the information we can get by that is the different areas or locations that the person visits, possibly the different objects with which it interacts. Now what you can see in this video is the sensor network point of view, what the whole sensor network is able to see. To see what every sensor node can actually see, you can look here. As the person moves over space and time, the background image changes. The reason is that the person changed from the field of view of one camera sensor node to the field of view of another camera sensor node. Now this is all the information we're actually getting. Basically we're getting a time-stamped sequence of image locations on a map. What we want to do is we want to get this input stream of low-level information and map it to higher-level activities. And during my PhD, I've actually designed a whole architecture that is able to do that. At the lower levels, you have a wireless sensor network deployed in a house or in other scenarios as well. It continuously monitors the people, gets the data, stores them. Data are filtered in real time and specific features are being extracted. Now, these features follow 2 paths. The first one has to do with automatically extracting activities out of these features and building the daily activity model of the person that we can use to find unusual activities or predict the activities of the person. And the other part has to do with the runtime interpretation of the low-level data to the higher-level activities. This means that as the low-level data are being recorded and are coming into the system, we want to have a way to map these activities at runtime into higher-level activity information. Now, the way the users actually can interact with the system is through their cell phones. They can pose specific queries like what are the latest locations that the person visited, what were the latest activities that the actual person were engaged into. So it's basically more of a safety check. Is everything okay? The second way they can interact is through activity summaries. Medical personnel or the family of the person can log into the system, check the latest activities, and make sure that everything is okay. The third one is that users can actually register with specific activities, and whenever this activity is detected, they will be automatically notified through an email or an SMS message. My work in this architecture has focused from the lower levels up to the higher levels. Yes?
This application library layer that you have says activity description library. Yes. So should we think of this as sort of a vertical thing that you're going after, or horizontally? That means it's very specific to that application?
It is a vertical thing that is going out there. What we want to do is we want to design these components, right, so that can be customized to specific deployment or specific activity we want to detect. What we actually want to do is we want to provide an application layer where we can have application developers customizing the system. Customizing the system in terms of the activities we detect and the services we provide. Now, what we eventually want to do is we want to get these application level descriptions and map them down to the sensor node level. And this is the main challenging part. And this is why we have to move to the parallel platform design, as I will motivate you in the next minutes.
So I understand the sort of grand challenge, but in your case, you have sensor activity that's going on. Mm-hmm. And then, so when you develop this application library, for example, did you develop it from looking at what you were getting going up, or did you develop it that this is what I wanted and push it down and said, okay, this is what I want the sensors to do?
Both ways. So the whole design process was both ways. We went both ways, up and down. The way we design the activities is a top-down approach. So given an activity we want to detect, we first decompose the activities into a sequence of very primitive actions. So basically get a high-level specification, we map it down to lower-level specifications of the activities. And then what we do is we follow a bottom-up approach. We're trying to instrument our sensor network with a set of sensors that can provide very basic information about these primitive actions that can happen, right? And then being able to detect these primitive actions, we can go incrementally up to the higher levels and map this low-level information to higher-level activities. So it's both ways. The actual design is top-down, but we also have the bottom-up approach in there as well. Now, my work has focused on designing power-aware platforms for monitoring people and getting the information, designing the software and the middleware that they require, interfacing different sensors and extracting features out of them. And of course, my work has focused on the higher levels in terms of efficient methods for extracting activity information and efficient methods for mapping incoming streams of low-level data to higher-level activities. Now, in this talk, I will focus on the lower levels. I will basically describe to you my contributions in the terms of the power-aware platform design. Yes?
I have to ask my standard sensor networks question. Sure. Which is, why is this a sensor network and not a centralized system? Because if you're in a house, you have plenty of power. You probably have a single hop networking to base station. Why build a sensor network?
So there are several answers to this one. The first one is that you don't only focus into a house. We didn't design the system just for assisted living. Assisted living is a driving application for us. We can go everywhere else. You can see this activity monitoring outside the house as well, at the city level, at whatever you want, Google Maps level, Windows Live search level, wherever you actually want to see that. Yes, I have to put both in there, right? Now, the other thing is that not many people will be willing to adjust this technology, to adopt this technology, if you tell them that they will have to drill holes, get wires in the house to basically power the sensor nodes. What you want to do is you want to have an actual person coming, getting a kit of 4 or 5 sensor nodes, putting them on the ceiling, putting them in specific places in the house, and he will be able to use the system. So it's basically easier for us to go into this type of applications. Yes?
So you won't ever have to change batteries?
What?
If you put sensor nodes on the ceilings, will you have to go change batteries?
That's why we need the power-aware platform design. That's why we need to guarantee that these actual sensor nodes can last for a long time. They can monitor the person for a long time. And whenever they don't have batteries, they can notify us to go and change the batteries. Yes, we're going to have to do it, but the whole goal is to be able to do this at long time intervals. For instance, I don't want someone to be going there every 2 days and changing the batteries. Like, not even PhD students do that in research deployments, right? Yes?
How long is long time? Is it like changing a light bulb, or it's every 5 years?
Well, if you ask me where you would like to go, I would say years, 2-3 years. If you ask me where we are right now, I will tell you days. But this is where we want to go. Yes?
Activities. So on your example, you had movement. And I don't notice, I know you see more mention this talk, but what types of activities? If you look at all extracting from a camera.
So we're talking, it's not about the camera, it's basically a moving dot, right? So a camera can give you way more than that. Now, typical activities that we've been detecting have to do with sleeping activities, bathroom activities at the lower level. At the higher level, one of the examples and the study cases we did was cooking activity. So if you have someone inside a kitchen and you monitor this person, he does something, you want to be able to find out if he's actually cooking or not. And it turns out to be a quite challenging problem because you might have, yes, go ahead.
Just from a dot. You're saying
Yes,
it's just
from a dot and a map.
Was there only one dot in the house?
There was only one dot. There were no pets in the house, and we did that so that we get good data out of that. Then, if you have multiple dots, you have the tracking problem. And there are other members in my group back at Yale University that are working on this problem, but of course the problem is not solved. And I'm not going to claim I've solved the problem. But in these deployments that we had, there was only one person living in the house.
So your example is stationary dot, in the bedroom you can assume sleep.
Yes, but cooking is way more general than that, right? Because in the kitchen you can have several different activities that might happen. And you might have cooking activity instances that range from 5 minutes preparing breakfast up to 1 hour. Yes. Yes. Exactly. So you don't need this answer, exactly. Yes.
So maybe you will answer this question later in your talk, and that's what it's fine. This is just follow up on Bill. Bill's, you said that you would like to go to months, and you are at days right now. So that's.
I would like to go to.
You would like to go to months,
Years
for changing batteries from days where you are now. So that's like 2 orders of magnitude. So,
yes, but
so how do we go there? I mean, maybe you can address it as a feature work.
So why are we in days right now? Because we are in research, right? And what we do is research prototype platforms. So the main goal there was not to minimize the power, to demonstrate design principles that can be used to drive this change of the 2 orders of magnitude, to go from these 2 days to the years. And this is not going to be done only by research, right? You need the industry as well in there that will come and redefine the design of the components that will allow you to do that. But beyond that, you need to explore specific design techniques, bottlenecks and trade-offs at the hardware level to be able to enable that. Yes?
Do you have a scenario why people would care about movement inside a house or outside a house?
I didn't get the whole question again.
Do you have an application scenario in which people would care about another person's movement inside a house or near the house?
Yes, I have my father and my mother that they continuously calling me and telling me, what are you doing, if you're getting enough sleep, if you're always eating, if you spend enough time at home. I have my advisor that he's crazy about getting the system into his mother-in-law because he lives alone. And actually we did that in Boston, Massachusetts, and he wants to make sure that she's okay, she will never fall off the stairs and break hands and stay there for days. So yes, I can find a lot of people that actually need that. This is in the context of assisted living. Now I can find a lot of people that might need something like that in security applications, military applications, surveillance applications, and so on. Okay, now this is the slide with the most questions every time I give this talk, so we deal with that. So again, one question that came up was, do you really want to do the centralized processing? Do you really want to get all this type of information, move it to a central processing engine and get the activity extraction? And the answer is no. Where we want to go is we do not want to bring the data to the interpretation mechanisms. We want to bring the interpretation mechanisms down to the data. And basically what we're trying to do is we're trying to push the computation as low as possible to the actual sensors. What we want to do is, as long as information is detected at the sensor node level, we want the sensor node itself to be able to summarize and interpret this information as soon as possible. Now, by doing that, we will be able to maximize the information reduction at the sensor node level, and we will be able to minimize the communication at the network level. But in order to be able to do that, we'll have to be able to provide the necessary processing power that will enable the sensor node to do this interpretation. And to do that, we have to move forward from the actual low-power platform design to a more power-aware platform design. People so far have been focusing on designing low-power sensor nodes. How? They basically get the components with the least power consumption, they put them together, and they get a low-power sensor node. And this has really demonstrated a lot of things, right? But the problem now is that very low-end microprocessors do not provide enough processing capabilities to do interesting things, especially in this context of applications. What we really want to do is we want to move on to the power-aware platform design, where we design sensor nodes with high dynamic range. Basically, whenever I want to design a sensor node that can provide me the power that I need to do the processing whenever I need to do that, but whenever I do not need this processing, I need the sensor node to be at a mode with the least possible amount of power consumption. And yes?
Okay, so there's a fundamental assumption here that communication is more expensive than computation.
It's not necessarily the case.
Okay, so what's the ratio? I mean, a byte of communication versus how many CPU cycles?
There's no standard ratio. Right now, when we started the sensor networks, we were like, don't do communication. Communication is highly expensive. Don't do anything. Now we're slightly shifting that, and we say that the actual computation that we do is comparable to the communication, right? And now where we're going to move is maybe at some point for specific times, for specific time intervals in the network lifetime, the computation might be more expensive. The computation might be more expensive than the actual communication, right? And this is why we have specific trade-offs at the hardware level that we have to exploit. In specific cases, depending on the amount of data that we're going to record, communication is going to be very expensive. You don't want to communicate row-level data information. You don't want to communicate every single bit of information you are recording. You want to maximize the information at the sensor node and then have a sensor network that operates on symbolic information.
Particularly in your home scenario.
Yes.
Putting a server, putting a very powerful computer that's plugged into power, plugged into the AC grid is cheap, yes, right, compared to any of these nodes. So it seems like the only time you ever want to do any computation on the node is if it's cheaper than getting the data off the node.
Yes.
Right? Then any time you cross that threshold, the right answer is, oh, am I correct?
Yes.
The right answer is always set it off that you can.
Yes, but the whole thing is that we're not going to always have this sensor network actually operating in the context of a house. We haven't been designing a system that is tailored to the assisted living application. It's not the assisted living application that we're after. It's a system that can monitor humans over space and time, and then can create an understanding of what they do. This means that it can be expanded outside the home case scenario. Like in the home case scenario, I agree with you. You don't even need to worry about power aware at the first place, right? You just plug it into the power, the sensor node itself, right? And you can put whatever you want.
I mean, we have a house in Utah that's got walls that are this thick, made out of stone. It's impossible to wire the house, right? So I understand you can't get power, you can't get network to every location you want a sensor, but I don't necessarily believe that you can't get within radio range of a fixed station. Any place that you are concerned with human activity, other than maybe in a wilderness area.
Like if you get it out to the city level, for instance, let's assume you wanna monitor the Microsoft campus.
Let me try to add to what Galen is asking you. So, in your communication cost, do you assume a static communication cost all the time in your design, or are you adapting to the topology of the network and then decide what needs to get computed on a node versus what needs to get communicated?
Well, you're going to have to adjust, and it's not only the topology of the network. Is you have a data-driven computation here, right? You have a data-driven, like the way humans move over space and time, they define the way you're actually getting data into your network. So you don't know when, where, and how much data you're going to have. So you're going to have to adjust at runtime. Given the amount of information you have, given the network traffic we have, and given the actual hardware you have to be able to answer this question at runtime. What is the best way to do that?
So I'm assuming you're going to tell us how you're going to do that, right? Because hardware is also evolving. If you look at, for example, Wi-Fi and Next, like a couple of years ago, and look at them now,
exactly,
the amount of power they consume and all the optimizations that have happened are vastly different, and it's totally
correct.
The power profile is very different, right?
But beyond this industry-driven improvement, you also have to come up with power-aware techniques that will use these components and create an additional 10x factor in terms of the power consumption. So if you give me an actual radio that is 10 times less, has 10 times less power consumption, you can also use some of the techniques I will describe here later to do it even more low power. Okay, great. So now my work and my contributions in this case of power-aware platform design have been focusing on the architectural implications, how we basically design these sensors to provide this high dynamic range. And in this talk, I will describe specific design techniques to basically combine the advanced processing power whenever we need it with extremely low power sleep modes. In addition to that, I will demonstrate how I will identify and quantify specific bottlenecks and trade-offs at the hardware level that can be exploited to create a more fine-grained power control of the platform. And these bottlenecks have to do with radios and have to do with processors as well, going back to your question. Now, these different design trade-offs, bottlenecks, and techniques that I'm going to be describing, I'm going to describe them in the context of the two sensor nodes I've actually built. The XYZ sensor node at Yale University. This is a single processor platform, but it goes from the simple 8-bit microprocessors up to the case of we use a 32-bit ARM7 TDMI-based processor that can operate from 2 megahertz up to 60 megahertz. Now, the key novelty in here is that we can combine this processing power with extremely low power sleep modes that a very low-end microprocessor can actually have. Now, the second platform I'm going to use is the mPlatform architecture that we designed here at Microsoft Research. And this architecture basically enables to put together in a single node application stack several different heterogeneous processors as well as several different heterogeneous radios, right? And in this case, there are several trade-offs that come on at the hardware level on how you interface these things together. How do you enable communications of these different processors and radios on the same stack to get an energy-efficient sensor node? But before I go into this more complex case, let me first focus on the single processor case where you have the XYZ. And here you can see the actual architecture. It's very similar to the architecture of any sensor node that you can see out there. The difference is that we use an ARM7 processor, and the processing power we get out of this allows us to extend the sensing subsystem with an actual camera. We can get images, store them in external RAM, and process them to find features. Now, the novelty of the sensor node does not lie on the processor that we use. It lies on the power subsystem. and the fact that we have incorporated a supervisor circuitry that allows to put the whole sensor node and not the actual processor into the deep sleep mode, into a deep sleep mode that is very comparable to the deep sleep mode of a single low-power microprocessor. But why is this important? This is important because, as I said before, you're not going to be always in need of this processing power. In most of the time, the wireless network might not have an event to process. So in that case, you're going to be in a mode that you consume the least possible amount of power. Now, the way software techniques are actually trying to do that is by putting the actual processor into one of the sleep modes that the processor offers. The problem is that when you try to use more advanced processors, like the ARM7 TDMI, these sleep modes are highly inefficient. For instance, here you can see the current consumption of the two different sleep modes of our processor. In the standby mode, the clock oscillation is completely stopped. In the halt mode, what happens is that the clock is still running, but it's blocked from several components. Now, if you see the current consumption in both cases is in terms of several milliamperes. So we're getting milliwatts of power consumption. Now, if you go to a lower-end microprocessor and you put it in a deep sleep mode, you're going to get current consumption that is in terms of microamps, 10 microamps. So we are operating in an order of magnitude higher than the lower-end microprocessors. And in order to have power-aware platforms, we have to bridge this gap. And the way I bridge this gap in XYZ is by designing this supervisor circuitry that allows the processor to completely turn off the whole sensor node. Now, the main thing here is the real-time clock that is directly powered by the batteries. This means that whatever happens in the system, as long as we have battery power, the real-time clock will be on. The other thing I want you to notice is that the real-time clock, through a square wave interrupt GPIO pin that it has, it is able to control the enable pin of the voltage regulator. At the same time, this enable pin is also controlled in software, in the microcontroller, by an actual GPIO pin. Now, what happens and how we actually use this system is the following. Initially, we turn on the sensor node. Now, momentarily, the actual voltage regulator will become on. Power will be given to the system, and the actual processor in software will take control of the enable pin. So it will guarantee that the actual sensor node is continuously on, operating on the data as it should be. Now, after some point, the microcontroller decides that it has to go to sleep mode. The first thing he has to do is program the real-time clock over the I2C about the actual time that he wants to go to sleep mode, and then turn off the regulator. And this would do it in software. Now, by turning off the regulator, the power to the whole sensor node is cut off. This means that the actual processor is not powered, the discrete components are not powered, and all the sensors are not powered. Now, during that time, we can achieve having a current consumption of approximately 30 microamps, basically one order of magnitude less current consumption than before. Now, after the pre-programmed amount of time has elapsed in the real-time clock, what happens is that the real-time clock will generate a square wave pulse in the enable pin of the regulator. This will momentarily enable the regulator, and this time we've measured it while designing. It's large enough to basically enable to the microprocessor to boot and gain control of the enable pin in software. In this case, this actual processor can turn off the whole sensor node, including himself, and then wake up independently. And by doing that, we can have a current consumption of approximately 30 microamps in deep sleep mode. So in that way, what we've actually achieved is combine this advanced processing power of a 32-bar microprocessor with an extremely deep sleep mode. But now someone, I'm pretty sure many of you are thinking of it right now, is how do you always know how much time you're going to go to sleep mode? For instance, if I have a sensor node inside the house, right? Someone leaves, there is no one in there, and I go to sleep mode. And then someone else comes into the house. I have to be able to know that there's someone in the house that I have to monitor, right? So the sensor node cannot do that completely independently of everything else. Now, in this case and in this design paradigm, you can think of a lower-end microprocessor that is continuously on, interfaced to a very small occupancy sensor, like a PIR sensor or an RFID sensor. Whenever this small circuit detects that there is someone in the house, it will automatically enable the voltage regulator, wake up the 32-bit processor with a more complex sensing modalities, and be able to do the monitoring. And this is something we can actually do in the context of the mPlatform. In the context of the mPlatform, a sensor node is basically a collection of boards. And every board has customized processing, sensing, and communication capabilities, right? Now, you can imagine one of these boards being the low-power microprocessor interfaced to the occupancy sensor. And you can imagine another board in here being the actual XYZ sensor node. So in that way, you can map these boards and create an application-specific node that can fully combine the advanced processing power of an ARM7 processor and extremely low power consumption. Now, of course, the mPlatform was not specifically designed for this. It's a way more flexible architecture that allows us to put many different heterogeneous components, including processors and radios together, find where the actual trade-offs are, and be able to exploit it. And one of the major design challenges in the case of the mPlatform architecture was when we combine several different heterogeneous processors together, we have the problem of being able to support data exchange between the processors. So in order to perform the task, the different processors will have to exchange data. And the way most people do that right now in the current state-of-the-art platforms is by using standard buses like I2C or SPI. Now, the problem of these buses is that they are extremely inefficient. For instance, you can imagine having two ARM processors operating at 60 megahertz and exchanging data over a serial I2C bus that operates at 400 kilohertz. It doesn't make any sense. In addition to that, if you have multiple processors, many of them might want to communicate at the same time. You don't want a communicating pair of processors to block any other communications that might want to take place at the same time. To deal with these problems, we've actually created a communication channel. And the main novelty of this communication channel architecture is that it allows to automatically adjust to the processing capabilities. This means the faster the processor they want to communicate, the faster the communication will take place. And the second thing it does, it can basically support multiple communicating pairs of processors at the same time. The way we're actually doing that is by enforcing the use of a CPLD on every board in this stack. Now, what the CPLD does, it basically abstracts the CPU from the actual parallel bus that connects the CPLDs across the different boards. Okay. It's a complex programmable logic device. It's basically generic hardware that you can write software to customize it to do a specific thing. If you are aware of FPGAs, field programmable gate arrays, it's something very similar but more at the low power domain. Now, the whole purpose of the CPLD, again, is to abstract the CPU from the actual bus. Whenever the CPU wants to communicate data, it will not go and directly access the bus. It will deliver the data to the CPLD and forget about it, go back to the sensors. Now, it's up to the CPLD to do the bus management, transfer the data to the receiving CPLD, and have the end-to-end communication. But in order to convince you that this meets our design guidelines, I have to tell you two things, very important things. The first one is how do you design this interface between the CPU and the CPLD? And the second one is how do you actually manage this bus? In the case of the CPU interface, we've opted to go with an asynchronous 8-bit parallel bus. The reason we used an asynchronous bus is an asynchronous protocol is the fact that it allows the CPLD to adjust to the processing capabilities of the processor without sharing any clock information with the processor. This means the faster the processor that we're actually interfacing to the CPLD, the faster the communication will take place between the CPLD and the processor. Basically, the whole performance depends on how fast the actual processor can toggle a set of GPIO pins. Now, in the second case, in the case of the bus management, our main goal was to create some fairness in terms of using the communication channel. When multiple communicating pairs wanted to exchange information, we wanted to be able to support that. And given this design guideline, what we decided to do was to use a TDMA-based approach. Basically, every board, every CPLD in the stack is assigned a unique address and a unique slot. Now, what happens is that this board can only communicate information when its slot is active. When its slot is not active, it will simply wait and listen for possible data. Now, the type of data we're actually sending on its time slot are 24 bits data because we're using a 24-bit bus. The first 8 bits are used for addressing. You can have unicast, broadcasting, and the rest 16 bits are the actual data. Now, here you can see the overall architecture as it has been designed and implemented on an actual CPLD. Initially, we have a CPU interface for doing the communication. The CPU can pass data to be transmitted or can set runtime parameters of the CPLD, such as the time slot, the number of slots, and so on. Now, as soon as a packet is actually being received by the CPU, it's stored in the transmission FIFO, and the TDMA transmitter will continuously check to see if there are packets. If there are packets, they will be fetched immediately, and when the slot of the CPLD becomes active, they will appear on the channel. Whenever the slot of the CPLD is not active, data will be automatically received, see if they're destined to the CPLD, and if yes, they will go into the reception FIFO, and the memory status signals will be updated. Now, this whole architecture has been implemented in Verilog HDL language, and it has been mapped into two different families, basically a single family, two different components of a single family of a Xilinx CPLD that allowed us to have this actual bus implementation running at maximum speeds of 68 megahertz or 45 megahertz. Now, having the ability to map this to actual hardware allowed us to use the mPlatform to move on and evaluate and see if we actually met the design guidelines. Yes? The CPLD. So it depends on the actual frequency that you're actually using. In the case of MSP430s, like lower-end processors, even 5 megahertz is good enough. In this case, you're going to have 5 milliwatts, which is almost the same as the processor. In the case of the ARM7, it has to go up to 16 megahertz and will consume 30 milliwatts. But the whole thing here is not that I'm trying to tell you use CPLDs to do this bus architecture. The reason we use CPLDs was because it was easy for us to reprogram the CPLD and test different ideas. In practice, what you're going to do is you're going to get this Verilog HDL specification and map it into an actual custom ASIC chip. This will drop the power consumption by 1 or 2 orders of magnitude and will increase the actual speed by 1 order of magnitude. So you basically solve that. So this is a demonstration of the design principle, yes.
So that kind of drop in order of magnitude you would see for computation, but isn't part of what this chip is doing sending signals over a wire between two motherboards, which that power you're not going to save on? So are you sure that estimate is correct?
No, what I'm trying to say here is that we can have this high efficient communication at a low power overhead. So this custom chip that you're going to make, it will be able to provide you this energy efficient, this low delay communication channel, right, that can support multiple communicating pairs of processors at the same time at a very small power overhead.
I understand that.
Yes.
When you tell me you're getting an order or two of magnitude savings by going to an ASIC chip, you've got two things that are consuming power. One is computation, and one is generating a strong enough signal to get between the motherboards. You will save on the first one, you won't save on the second one. So if the second one's an important component of your power consumption, you won't actually be getting that yes. amount of savings.
First of all, when I say an order of magnitude low power component, I don't mean for the whole system. I mean for the actual chip, going from the CPLD to the custom ASIC chip. Do you understand what I'm trying to say?
Yes, but the CPLD is driving signal between motherboards. Correct. Is that not correct?
Correct.
How much power is that?
How much power does this take? Well, in our cases, where we measured the power for driving this actual, the average was for the CPLD from 5 milliwatts to 13 milliwatts.
13 milliwatts.
Yes.
Okay, so if you drop the 30 to 3, then what Stuart's talking about is your total goes from 45 to 18, so you get a third.
No, what I mean is that you're going to drop this 13 milliwatts, hopefully down to microwatts, or even a few milliwatts, like 1 milliwatt or something like that, because this is based on the technology that we actually used to implement this specific chip. It's based on the ASIC technology. Excuse me?
Well, again, Stuart's trying to ask, there's two different components of the power. There's the processing power in the ASIC or in the TTL or whatever it is.
Yes. Now, the actual power I'm referring to you has been measured taking into account both. So what we did is we had the actual boards transferring data, right? The actual, yes, computation plus the actual power for driving the actual bus.
Okay. So do you know what fraction was the power to drive the bus?
No, I don't know that.
Because
I haven't measured
that probably won't go down with better.
Correct. Oh, correct. I agree with that.
So why have the floor? I've been wondering for what's the energy capacity of a battery?
Also what?
How many joules in the battery?
Like 2,000 joules. I can't remember exactly. I can remember like it's like.
Can you tell me watt hours if I can convert?
It's like 2,800 milliampere hours or something, if I remember well. It depends on how many batteries you use and.
Well, I mean, so like one battery is less than
Between
3 watt hours.
1,400 to I mean, it depends on the type of battery.
2,800 something like that. Typically it's 2,800 milliampere hours.
Milliamp hours of 1.5 volts.
This depends. It might be 2.5, it might be 3.3, and it might be like.
Double A batteries are 1.5 volts.
Not all of them.
Yeah, what, starting
Okay,
from
they're supposed to
1.8.
be. It says right here, 1.5 volts.
No, but
Usually the brand new one is 1.8.
Okay,
Yes, then afterward, the voltage will drop.
yeah, okay. Alright. Okay, let's.
and some of the rechargeable ones are always on the below.
Transport.
And it's about.
I guess I'm seriously running out of time, or is it just my idea?
You have until 12.
Oh, I have until 12. Okay, good. If you need it, yes. I see Victor bubbling really. So what you can actually see here is the evaluation we did on the actual mPlatform in terms of the end-to-end delay. Now, comparing with I2C, we're actually better, but this is not a significant measure of that we did well, right? It's I2C, it's highly inefficient, we know that. The nice thing is that depending on the communicating pair of processors, we can automatically adjust the end-to-end delay. The faster the processors we're using, the faster the actual end-to-end delay will be. And with respect to the I2C, when ARM7's processors are used, we might go down by 90%, and when MSP430's processors are used, we might go down by 40%. Now, the other thing that was nice was the fact that we could use a large number of slots, basically a large number of processors, without significantly adding delay, increasing the end-to-end delay in terms of the communication. So here you can see the percentage of the increase in the end-to-end communication delay for different classes of processors and for different data size being exchanged. We can easily go up to 10 slots. This means supporting 10 different processors, and the maximum increase in terms of the end-to-end delay is going to be 0.25%. The reason why I actually achieve that is because we can have the actual CPLD multiplexing the TDMA bus really, really fast by taking advantage of, by exploiting the hardware parallelism, while the processor takes a lot of time to basically deliver the data to the CPLD. And this can be more easily seen here, which is the run-reverse question that shows the effect of the clock frequency with respect to the end-to-end delay. Now, depending on the class of the processor we're using, there are specific sweet spots above which does not make sense to increase the CPLD clock frequency. In the case of the MSP430 with 5 MHz, we're all set. The actual bottleneck becomes the processor and not the actual bus management. In the case of the ARM7, this has to be increased up to 16 MHz. Now, summarizing this communication channel, what it basically does, it abstracts the channel from the CPU, it decouples the CPU from the channel, and it allows us through the synchronous interface to automatically adjust to the processing capabilities of the CPU. The faster the CPUs, the lower the end-to-end delay. The last thing you can actually do is that it can support multiple or near real-time multiple communication across different sets of sensors. Now, sure, yeah.
You have to add more and more TDMA slots as the number of boards goes up, right?
This is what I did here.
Are you burning power on each of those boards listening for a possible message?
Yes, you have to burn this power. And there's a lot of things in there of how you can actually conserve power in terms of the slots, right? There's a whole interesting trade-offs in there of how you can assign multiple slots to boards that want to transmit more information, or deduct, basically remove some slots from some boards that they don't want to transmit the information. But I haven't really gone into the details of that.
It seems like unless the bus is very highly utilized, it seems like that's the major place you're burning power. In other words, that
Yes.
the cost per byte is going to be totally swamped by the cost per idle listening.
Like, we don't, the way we, it depends on if we're talking about the CPLDs or the actual chips. In the general case, yes, you're right. Like, if you have to stay for a long time there and listen to it, then you're going to increase your power as well, because the actual round-robin cycle for waiting for your slot is going to be increased. Correct.
Waiting to know, is there a rendezvous mechanism for knowing that if there's any message that anybody's planning on sending, or are you just listening?
Oh, there are specific time slots. So we have a global clock going across the different stacks, and we know when the time slot starts and stops, and we know if someone puts data on the actual bus or not. There are mechanisms to be able to know that.
That's a little bit of a thinking question, which is how do you know if anybody is transmitting something on?
Oh, we have an actual, like, these are details that I didn't mention. We have some actual pins that we're using across the boards to signify if for a specific time slot someone is actually sending the data. Now, who is sending the data, we can find out by the addressing field. We have an addressing field in the package that we're transforming to find out.
and set and then go back to sleep?
No, every time a new slot comes up, we just see if there is a packet in there. If there's a packet, we get it, and we do the address decoding. If there's not, we just move on. Okay. Now, going back to the communication channel, this communication channel architecture, the main problem it was trying to basically address was how do we exchange the data across the different processors. But as Victor previously said, you also have the problem with the multiple radio components. So given a specific amount of data you want to communicate, and possibly given different radios that you support, how do you actually schedule this communication in an energy efficient way? So for instance, in the mPlatform architecture, we had two radios. The 15.4 radio, that is a low power radio, but provides very low data rates. And we had the 802.11.b, which was a very high power radio on the one hand, but with extremely high data rates, which makes it more energy efficient. So what people tend to do is they say, okay, since the high power radio is more energy efficient, we can easily compute the amount of data bytes we want to transmit, above which it makes sense to use the Wi-Fi radio. My work here has focused on demonstrating and quantifying the fact that this is not true in the actual hardware, because the energy efficiency of the radio also depends on how you embed your radio into your platform, what the interface of the radio is, and how you actually interface your radio to the actual processors. And in addition to that, I also try to quantify how the runtime network parameters, such as background network traffic, will have an effect on the actual energy efficiency of the radio, and therefore change this decision point. Now, the first thing I want to show you is the power profile of both radios so that you can see where the actual bottlenecks are. Here you can see the power profile for sending different packets of different sizes in the case of the 15.4 radio. X-axis is time, Y-axis is the current. Now, here you can clearly see the states. Initially, we have to write the bytes to the radio. Then there's a TX calibration stage. Then we have a transmission stage where the actual packet appears on the channel. Then RX calibration, and then we go back to the default RX state. Now, the thing I want you to notice here is that as we, yes?
Suggesting that hardware is going to make a determination about which radio to use?
No, I'm suggesting that it's going to play a very important role. You have to be able to exploit the trade-offs at the hardware level to be able to make an energy efficient decision. If you ignore the hardware, then your decision might be totally wrong. Now, what happens here, and what I want you to notice is that as we increase the number of bytes that we're actually sending, as we increase the payload size, two times are increasing. The time that it takes to write the packet down to the radio and the time it takes to transmit the actual packet. Now, this time, this radio I/O communication can be up to 20% of the airtime. By simply considering the energy per bit in terms of power consumption and data rates, is at least inaccurate in this case of the 15.4 radio. But when it really makes a lot of impact and has a lot of impact is in the case of the 802.11b radio. And here you can see the same power profile for the 802.11 when an MSP430 at 6 MHz is used to drive the radio. And here again, you can see when the actual processor is writing the packet, how much time and how much power you need. And you can actually see when the actual transmission of the packet happens. So these spikes correspond to the transmission. Now, as you can see, the dominant time here in terms of the packet transmission is not the actual transmission time. It's not the time we have to spend so that the actual packet appears on the air. The dominant time and the dominant source of energy consumption for the radio is the radio processor I/O interface. It's the time we actually spend transmitting the actual packets to the radio. And this is very significant in terms of the overall energy consumption of the radio. Now, by using this type of information, we were able to quantify the time and the energy consumption that would be required to transmit different data sizes with both radios. And it's not just the bus. It's first one is the bus. The second one is the radio interface and the complexity of the radio interface. And the third thing is how fast your processor is in terms of driving the radio. Exactly. Because many people out there would assume that it's a Wi-Fi radio, and not they will assume they're actually doing it. It's a Wi-Fi radio, it's energy efficient, so we just use it in our hardware with the same processor, and we take advantage of its energy efficiency. And in practice, this doesn't work. You have to work really hard to get this energy efficiency out of it. Exactly.
You can't get the efficiency out of it.
Exactly.
You can't drive it hard enough because it's so much faster.
Exactly. And in addition to that, during that time, it has a very high power consumption that you have to be able to support. And you have to take this into account. So what people do is they simply take into account this part and completely ignore this one, which corresponds to a whole different aspect of the energy consumption, the energy efficiency of the radio. Now, the interesting things come up is basically what you just described. If we here you can see the transmission time for different packet sizes. Now, what you can see here is that the time it takes for the Wi-Fi to transmit almost any number of bytes is significantly less than the Zigbee, which makes it really promising in terms of that the Wi-Fi will also be more energy efficient, right? However, when you go up to the energy comparison, you're going to see that you have the total inverse effect. The reason is that due to this inefficient radio I/O interface, we'll have to support the high power consumption of the radio for a long time. This means we don't take advantage of the energy efficiency of the Wi-Fi in practice. And this makes the Wi-Fi always less energy efficient. Yes?
Take into account collisions and the power consumption required when you need to respond to a collision?
Correct. So far, I'm not talking about network. There is no network. There is only a single sensor node trying to transmit a packet. And the reason why I did that in this case is because I want to demonstrate the inefficiency in the processor radio interface. Now, what is coming up is also a quantification of what you just said. The effect of the back-off mechanisms and the fact that you have to retransmit a packet in the case of network congestion. There is a significant part there that is coming up right away. So basically, what this says is that you cannot use any processor to take advantage of the energy efficiency. You have to work really hard in terms of the interface. You have to match the radio and the processors. So the main question now is that, is there a crossover point at the end of the day, or the decision is typical? And the answer is, yes, there is a crossover point, as long as you properly match processor and radios. For instance, here, the worst case you get it when you drive the Wi-Fi using the low-end microprocessor. Now, in the green line, when you use an actual ARM7, this whole energy consumption goes significantly down. The reason it goes down is because we have a much faster radio I/O interface. Therefore, we have to support the high power consumption of the Wi-Fi radio significantly less amount of time. If we use a PXA processor, then this energy even drops down more. And now you can start seeing the actual trade-off, the actual sweet spots between the 15.4 radio and the actual Wi-Fi. So here, in approximately 1 million bytes, above this 1 million bytes, it makes more sense, it's more energy efficient for your system to use the Wi-Fi radio rather than the actual 15.4. And of course, the faster the processor we use to control the Wi-Fi radio, the actual sweet spot starts becoming smaller and smaller. Yes?
Small packet sizes, you just want to use the Zigbee and nothing else matters?
It's not actually the case, because then it comes back to what the previous question was. It turns out that for small packets and small number of data, the 15.4 will be better, right? Now, when network congestion might come into the game, you don't know that. The reason is that the energy efficiency of the low power radio is going to change. The more backoffs you have, because of the high network traffic, will basically might double or even triple the energy consumption of the 15.4 radio. So it might even more affect these sweet spots. But in general, this is the main concept. It will affect it if you have a lot of data traffic, but you have to remember that the actual MAC mechanism of the 802.11 is a way faster and more efficient mechanism than the actual 15.4. And you will be able to see that right away. So right now, what I'm talking about is that we have to do this matching between the processor and the radio. And the second thing that comes up is that it's not just enough to compare the energy efficiency of the radios. The reason is that we have to pair these radios with specific processors. So instead of comparing radios, we have to compare the energy efficiency between processor radio pairs. Now, as many of you have been asking is, what happens when you have network traffic? What happens when you have network congestion? And in this case, what we did is we ran several experiments and we recorded a lot of detailed time and power information to characterize the effect of several network parameters on the energy efficiency of the radios. What we did is we tried to simulate a one-hop network neighborhood. Basically, what we did is we scaled the number of nodes from 1 up to 5, where in each experiment, every node was transmitting 1,000 packets. Now, we tested several network parameters that had to do with the number of nodes, the transmission period which we were sending the packets, and the actual size of the packets. So small packets, medium-sized packets, and large packets. Now, at every experiment, one sensor node was directly interfaced to a data acquisition card, and we've been recording detailed information about the power and time. What you can see here is the empirical cumulative distribution function of the single packet transmission time in the case of the 802.11 radio when this is driven by the MSP430 processor. And going back to your comment, you can see that this lower end processor cannot really put any serious workload on the Wi-Fi MAC because the Wi-Fi MAC is very, very efficient and the processor is very inefficient in terms of delivering very fast the data. So the actual packet transmission time remains almost the same across all the different network parameters. However, when you go to the case of the 15.4, things change. So here, if you see what happens across different nodes and for a given packet size, as we decrease the packet transmission period, is that initially we have absolutely no skew, constant packet transmission time. As we get more network traffic, in the case of 5 and 4 nodes, we start getting significant skews. And as we reduce the packet transmission time, these skews get even larger and larger and larger. Now, getting 2 or 3 times higher packet transmission time means that we get also higher energy consumption on the radio. And the same thing can not only be seen across different packet transmission times, it can also be seen across different packet sizes. The smaller the packets we use, the less the backoffs, so the less the actual energy consumption. Now, what this led us, basically made us ask ourselves is, at the end of the day, can we just decide which radio to use and which network parameters to use in a completely offline way or not? And the way we did that to answer these questions was to compute the energy dissipation for transmitting 100,000 bytes for all the different network parameters that I presented before. What I did is, for every combination, I computed the average energy dissipation for a single packet. Now, using this average energy dissipation, I computed the overall energy that would be required. This is pure computation, not actual measurements. I computed the actual energy that would require to transmit the 100,000 bytes across different network parameter values. Now, what you can see here is that in the beginning, where there's no network traffic, it makes more sense to use maximum size packets. You pack more information into a single packet, therefore you get more energy efficient. However, when the actual network traffic increases, using maximum packet sizes is an extremely inefficient way of transmitting the information. In the worst case here, you can actually have 50% energy savings by simply using medium-sized packets, 50 bytes instead of 100 bytes. And what you can see here is that the actual energy dissipation of the radio when maximum size packets are used is very close to the energy efficiency of basically having minimum size packets. Therefore, what this shows is that the actual network parameters, the backoff mechanism, and the efficiency of your MAC layer can have a significant impact on the overall energy efficiency of the radio and therefore on how you design which radio to use. And hopefully I won't go until 12. So here you can see, yes?
It seems like this is really only half the story because
yes, it is.
The problem is that with low-power radios, the energy for sitting there waiting to receive a packet is almost as high as transmitting a packet. And so it seems a little misleading to say that, oh, we're only spending 1 joule during this 10 microsecond slot we're transmitting because it ignores the fact that somebody has to sit there for 30 seconds waiting for you to transmit.
I absolutely agree with you, and your point is valid, but this is not the only, let's say, gray spot in there. There are way more gray spots. And the main question, we have to study this effect, and we have to take this effect into account, but the main question that comes up now is how we can actually expose these different trade-offs at the software level so that the software level can actually take advantage of them at runtime and make the decisions. Right now, I've been demonstrating and quantifying in terms of the radio network performance some trade-offs and parameters that will affect the energy efficiency, right? But being able to use that at runtime in software is also another very important problem that we don't know, we don't understand fully how to do it right now.
Excuse me? It's exposing the right information. I mean, there's a mission that's looking at dynamically transitioning 802.11 devices between multiple power states at runtime by exposing an interface to applications.
Yes, definitely. Like if you look in every scheduling application, it basically takes advantage of the power model and tries to use this power model to do the scheduling. The problem is that
it's not that complicated, but go ahead.
It's not that complicated? I like that. Okay, we can talk about this more later. Yeah, okay, good. So As a recap, what I've been trying to demonstrate here was specific design principles as well as how we can exploit specific bottlenecks and trade-offs for creating more high dynamic range power-aware platforms for sensor networks. First thing I did, I demonstrated how in the context of XYZ we combined advanced processing with extremely low power sleep modes. Then I presented to you in the context of the mPlatform the communication channel architecture that can have really small end-to-end delays in terms of communication across heterogeneous processors. Based on the DMA-based approach. And then I quantified to you some of the trade-offs at the hardware level and at the network level with respect to the energy efficiency of the radio. Now, the whole goal of this is what I just described, is to be able to create a very detailed power model that can be exposed to the software and scheduling techniques so that we can take advantage of the lower level power control to create more energy efficient application scheduling on the platform. And one work that has been actually trying to use part of our results to do that. It's going to be appearing in the Design Automation Conference this summer. Now, besides quantifying, just simply quantifying several of the radio aspects, we also got some pretty good lessons out of it that were mentioned before. The first one is that we have to work hard to get the efficiency of the radio, to be able to take advantage of the energy efficient radios. To remove this need for matching the processors to the radios, the first thing we have to do is create radios with similar interface. Remove this complex internal buffer management that the Wi-Fi radio has that requires the low-end processor to spend a lot of time driving the radio. And the second thing that also makes more sense is, as Victor Bachl noted before, create low-power 802.11. And low-power 802.11s have actually been proposed over the last few years, and they're a first step towards this direction. Now, the other thing is that even though we might not have these properties, we are actually able to interface low power processors to high power radios and take advantage of them in a way that is similar to the communication channel architecture that I presented before. What we need is basically a radio abstraction chip that on the one way it can have an asynchronous interface for getting the data from the microprocessors, and on the other end it can have a very high speed interface that can drive really, really fast the 802.11 radio and basically take advantage of this energy its energy efficiency. So in that way, even the current radios and the current low power microcontrollers can be used together in an energy efficient way. The other thing that it's really interesting out there to exploit is how we can take advantage of the reconfigurability of FPGAs and CPLDs on the actual platform to create this high dynamic range of operation. For instance, if we're having a CPLD on a platform, at different points in time, we can use this as a dedicated processing unit, as an I/O device, or even as a storage architecture. And being able to know how we design this, where the trade-offs are, and how we can change this functionality at runtime, it's a very interesting thing to look at. Again, the overall goal we're actually looking at is creating energy-efficient platforms for general-purpose computing. Create a platform that can be configured in software to work as a very advanced processing node, and at the same time, be changed in runtime to operate as a very low-power sensor node. And here I will conclude my talk, and I'm just 5 minutes over time, I guess. Go ahead.
So, mobile phone providers have had to deal with low-power communication for a long time, and they do very different types of networking. And do you do any comparison to the types of
yes. First of all, we use totally different radios, and we have totally different processors and interfaces. Therefore, the trade-offs in these two cases are totally different in the sense that we operate in a totally different power domain. But as far as I know, there have been discussions to share the information we got and some of the results and trade-offs we quantified here, to share them with people from the cell phone areas and get some feedback from them. But right now, no, I don't have a direct comparison between cell phone work and our work in terms of actual numbers or actual techniques. And the main difference there is that the whole power domain that we operate is completely different. However, some higher level scheduling techniques might still apply. My work so far has been focusing on how to quantify and take advantage of the trade-offs at this power domain to better schedule the applications and the communication later.
Different Macs. Macs consume different the scheduling. There are two different kinds of Macs for Wi-Fi and the radius is looking at versus cell phones.
Can you explain that, Glenn? Oh,
access control.
not message authentication. But
The security guys. I have a question.
Yeah.
Could you talk about related work more?
I could talk about it.
Could you talk about
Yes.
related work?
So here's the one thing that comes up all the time. For instance, you say that you've been designing a communication channel architecture, right? And someone says, can you talk us about the related work? This comes up all the time. You can think of anything that has been done in the past that uses a set of processors and starts to communicate, from actual laptops to desktop computers to everything, from PCI buses to every other type of bus you can actually imagine. What is different here is the fact that we try to exploit some specific stripped-down versions of these buses in this power domain and in the concept of the wireless sensor networks. So the main difference with the previous approaches and the typical computer architecture is the power domain at which we operate. And it's a very interesting power domain of identifying where the sweet spots are and what are the optimal bus configuration and bus management techniques. So it's a power domain that makes a difference. Yes?
So I'll follow up on John. So what you think here is the methodology new or the findings new? I understand you're talking about...
It's both. Where we're going to go is both. First of all, several of the findings are new, especially in the wireless sensor networks community. So in some cases, we're exploiting techniques that are well known in the Wi-Fi, but we're bringing them down in the power domain. But where we want to go is we want to design automated methodologies for doing that. We want to exploit the trade-offs, and we have a specific methodology of exposing these trade-offs to the software and middleware, right, where the methodology comes into the game, so that we can use these trade-offs to have energy-efficient either communication or processing scheduling. So it's both that comes into the game, on how you probe, how you get the data at runtime, and how can you use this data at runtime to do the scheduling. Yes?
Two really quick questions I'll try. Sorry. So the first is, a lot of these felt like micro benchmarks. I'm wondering how they fit into the larger picture of the system energy utilization. And the second related question is that you said you were between 2 and 3 orders of magnitude away from where you are and where you want to be. I'm wondering if you have any intuition for where that's going to come from.
Yes, well, where this is going to come from. So which one question should I answer first? So the last one was about the order of magnitude. The first one was outside the context, yes. So far, we haven't been using these results in the context of an application and trying to actually do the scheduling. So far, we've been only focusing on the hardware level and where the trade-offs are, where the bottlenecks are, and how we can take advantage of them. So this is the next step that we have to go, and we have to take advantage of these findings to do what you're actually saying in the context of an application. The second thing is how we can actually fill the gap. I don't think we're going to fill the gap in the next year or 2 years. So it's not something that I can directly give you an answer. I can only give you directions how you can do that. The first thing is that we first have to hope for industry to create more sensor networks-driven processors, and they can do that. They can give us more high dynamic range processors and radios. And they need our help to give them feedback in terms of how they actually design that. The second thing is that behind this industry-driven chip process, we also have to get techniques to expand this high dynamic range. And the extremely deep sleep modes that I mentioned before was one way to do that. And what I want to do is I want to move on and use either more reconfigurable components, CPLDs or FPGAs, right, that can later be customized chips that will allow me at a very low power overhead to quickly switch between different modes. But it's a balance between industry and between complementary techniques at the architecture level to be able to support this high dynamic range. Now, how long is this going to take? I cannot give you a time diagram about that. Yes?
One of the questions Jeremy asked before, like about the trade-off in a sense between the listening power you burn and kind of your optimizations in the hardware. Like what's the relative potential you see in kind of trying to come up with better sleep, wake up scheduling techniques like on the protocol level as opposed to trying to optimize the hardware? Like where do you get the 10 years of lifetime from?
When you combine all this together, and this is what I was trying to say in the beginning, it's not about optimizing at the hardware, it's not about optimizing at the application, it's not about optimizing at the Mac or the software. Right. You have to have a cross-layer approach. The purpose where the hardware comes is to meet the application requirements. Now, you have to meet the application requirements, you have to do this at a minimum power overhead. So you have to really do a good job at the hardware level to really exploit where the trade-offs are, understand them, and be able to create a very fine-grained power model of your underlying hardware. Now, this fine-grained power model might change according to your software or your application. then you use this in your scheduling techniques to do that.
I think I appreciate this. So this is great, but I'm just asking because let's assume that because the protocols for listening and kind of waking up and sleeping are so poor that you burn, I don't know, 99.9% of your battery anyway, right? Then it just doesn't seem to be the right trade-off to focus on. I'm not saying it is like this, but
you mean, are you referring to the specific protocols that have been produced for duty cycling that? Yes. And many of the reasons why they're inefficient is because they don't understand what happens in the underlying layers. They don't understand many of these protocols that switching modes on a processor on a radio takes a lot of power consumption. They don't understand what is the efficient way to switch between these modes. The other thing they don't understand is that you cannot just go to any sleep mode anytime. The time you want to spend there is extremely important. So if they don't exploit these power modeling techniques, they will not ever be able to do a really good job in terms of energy efficiency.
In other words, you're saying it really requires both. It requires
yes. It's a circular design paradigm. You have to go back and forth all the time. Yes.
I'm curious about your use of cameras to detect people in terms of both. Is the choice because of the cost of the hardware or the cost in terms of power usage versus other?
Yes. So if you look out there in the terms of sensors you can actually use, you can either going to use sensors that provide very primitive information, like motion sensors, that you cannot do much with them, or cameras that will provide a lot of information. Now, what we want to do is we want to operate somewhere in between. And we use the cameras to simulate a sensor that works in between. So I don't do any complex image processing. What I do is I basically abstract a person as a dot based on its motion. And what I'm doing is I'm basically having a moving dot over time. This is the only thing I'm getting out of the cameras. Now, the reason we decided to use cameras was because it's a very flexible sensing modality. Whenever we decide that we want another feature to be used for this macro-scale human activity detection, we can change our code to use the exact same hardware to do more complex processing and get more features out of them.
How are they though in power usage? I mean, is a camera a much more power-hungry thing than a motion detector?
Correct. Excuse me? Well, if you use a VGA cell phone camera, it's very expensive. It's milliwatts. But where we actually want to get is, and the type of sensors we're actually simulating, if I find this log list of slides, is to go to a specific set of cameras that are called address event cameras. And here you can see one of them. Now, this is the actual address event camera. It's a research prototype interfaced on the XYZ sensor node. Now, these cameras are totally different from the cameras you know. In the CMOS cameras, you have to completely go to the camera, get images, and process the images to find events of interest. Now, these cameras have all the processing you need in the pixel on a per pixel basis. Every pixel operates independently of every other pixel. And you design this pixel to detect a specific feature, for instance, motion, edge, or something else. Now, whenever in each pixel this event is being detected, and an interrupt will be given to your processor saying that I had this actual event. Now, by doing that, you can extract the features you want in an event-driven way without getting images and without doing any complex processing. Now, the nice thing is that this type of cameras don't have milliwatts of power consumption. They have microwatts of power consumption. So basically, we've been using VGA cell phone cameras to go to this power level. And this is where we want to reach. And actually designing sensor nodes that can operate in this design paradigm is amazing.
So, given the time, I think we should wrap this up.
Yes.
Because even though Dimitri has another talk, and you can see that it's got a behavior
It's
scope
like 77 slides, so it's 2 more hours, easily.
Let's wrap this up. And actually, you probably have about 5 or 10 minutes before going to lunch. So people have other questions.
Okay. Thank you.